Ultimately, this is about two questions. What are the most fundamental constituents of matter, and what are their most fundamental interactions? Exploring the answers to these questions is an adventure between experiment and theory. On the one hand, we make experiments probing the most fundamental forces of nature. And on the other hand, we use theory to make sense of the results of these experiments to propose some unifying understanding and to suggest follow-up experiments to verify or falsify whether these proposals are correct by comparing the predictions of the theory with the experimental results. I myself stand on the side of my son August here. I'm a theorist. I make predictions to test our understanding of the forces of nature under the most extreme conditions, using the largest experiments that were ever built to discover what was previously unknown in the sense that we've so beautifully heard about before. But before coming to the unknown, let me talk about what we know. Let me take you on a journey to, in particular, how we know what we know. Zooming into matter, such as this block of wood, we find that it is made out of atoms. If we have today's machineries, such as a scanning tunneling microscope, we can even see those atoms. Each individual orange blob here is one carbon atom. They are very small, less than a nanometer, so a billionth part of a meter. However, this is as far as a microscope will get us. The Greek word atomos, from which the atom is derived, means uncuttable. And the idea that all of matter should be made from tiny, uncuttable pieces goes back to many different ancient civilizations. However, atoms themselves are cuttable. But how can we look into this? One way to do this is to throw stuff at these atoms, throw other particles at them, at what is called a scattering experiment. The challenge is then to reconstruct how the target looked by only observing the pieces of pie at the wall behind it. But to do this, we need some theory explaining how the target interacts with the projectile. In 1909, Rutherford, Marsden, and Geiger did this scattering experiment, scattering some alpha particles of atoms of gold. They found, as formulated by Rutherford 2 years later, that the atom is mostly empty. Most of its mass is concentrated in a tiny nucleus, less than a thousandth part of the atom in diameter. Around this nucleus, we have electrons, and they are really uncuttable according to our current understanding. They are really indivisible, or as we call them, elemental particles. The negatively charged electrons are bound to the positively charged nucleus via the electromagnetic interaction. And this interaction is carried by the photon. This is the force that gives a unified description of both magnets, electricity, and light in 4 short equations that bear Maxwell's name. These equations are very well tested. They give us, for example, the radio. But if you combine these very well-tested equations with some other very well-tested equations, Newton's equations of motion, you get something ridiculous. You get the prediction that the electron should just fall into the nucleus. So clearly something was wrong with our understanding. The solution here came in the form of Niels Bohr, who proposed that the movement of those electrons should not be governed by the well-established Newtonian equations, but it should be following the much newer laws of quantum mechanics. And this is how he formulated his Nobel Prize-winning model of the atom that we know today. Later, this was expanded to the theory of quantum electrodynamics. The nucleus, as we can find with further scattering experiments, is built up from protons and neutrons, the neutron having been found by James Chadwick in 1932. The neutron was moreover found to be able to decay in a radioactive beta decay, producing a proton and an electron. However, as this was observed, this appeared to violate conservation laws, in particular of energy. It's a very deeply held belief, and a much tested one in physics, that we can't just create energy out of nothing. We can only ever transform one form of energy into another kind. Niels Bohr was actually willing to throw the conservation of energy out of the window, having invented, together with others, invented quantum mechanics, which had already thrown other things out of the window. But Wolfgang Pauli believed in the conservation of energy, and he postulated that there must be a new particle, a particle that carries away the missing energy and which is interacting so weakly with everything else that it has escaped all previous detections. And indeed, in 1956, Cohen and Raines discovered this particle called the neutrino. With a bit of lack of imagination, one can say this interaction, the second of the fundamental interactions of nature, was called the weak interaction. Now, zooming further in, it was found that protons and neutrons themselves are built from quarks, from up quarks and down quarks that are bound by the strong interaction which is carried by gluons. This can be described by quantum chromodynamics, and those gluons carry the third of the four known fundamental forces of nature. So far, we have encountered the photon, which carries the electromagnetic force, the gluon carrying the color force of the previous page, and then we found the four matter particles, the up and down quark from the nucleus of atoms, the electron, and this quite hard to detect neutrino. However, also other particles were found, some heavier copies of these previous ones. Now, you might wonder, why should we have those? And you'll be in good company. At the discovery of the muon, physicist Rabi famously exclaimed, "Who ordered that?" Now, based on the particles that were known at the time, Glashow, Weinberg, and Salem, as well as others, proposed a theory that describes the fundamental interactions unifying quantum electrodynamics, the weak interaction, and quantum chromodynamics in what is called the standard model of particle physics. At least in a schematic form, the equations governing this theory are so short that you can even print them on a coffee mug. However, there was a flaw, maybe, or a feature of this proposal. It needed the existence of several further particles that hadn't been discovered yet. And they were thus predicted by this theory. These are the W and Z bosons, predicted, found then finally in 1983, the top quark discovered in 1995, and the tau neutrino discovered in 2000, as well as the Higgs boson, which gives all of those particles their mass. To discover the Higgs boson, the Large Hadron Collider was built. An unbelievably large accelerator of particles to then scatter them with a circumference of 27 kilometers. It took almost 50 years until from the original proposal of the Higgs particle by Peter Higgs and others to its discovery at the LHC in 2012. The Higgs particle was found as this slightly more, let's say, over density, slightly more scattering events at a particular energy than to the left of the right, as a slight bump, but Nobel Prize winning bump, over a large background. So far, we've looked to the very small. We've seen 3 of the most fundamental forces of nature. The fourth known fundamental force of nature is gravity. And to see this, we need to zoom out. Already in the 17th century, Isaac Newton realized that the same forces that make apples fall are governing the motion of the planets in our solar system. More than 100 years later, Alexis Bohr used the equations proposed by Newton to predict where the newly discovered planet Uranus was going to go next, based on where it had been before. However, subsequent observations showed some deviation between where this planet was supposed to be, according to our best knowledge of gravity and the other planets, and where it was actually. Now, one could say, let's just get rid of this equation, it must be wrong. However, this is not what Aubin Le Verrier did. He postulated that there should be another, not yet seen planet, that he could even determine where it should be by just requiring that it explains how Uranus behaves according to the mutual attraction by gravity. Le Verrier sent this prediction to Johann Galle at the Berlin Observatory, and in the night after receiving the letter with the prediction, he found this new planet within a degree of where it was predicted to be. And this is how Neptune, the 8th planet in our solar system, was discovered. Needless to say, this was a huge confirmation of Newton's theory of gravity. A decade later, Le Verrier found another deviation. He found that the motion of the innermost planet, Mercury, was 10% off. And he proposed another planet to fix this one. The planet which was later called Vulcan. So who's heard of this planet before? Only the Star Wars fans, maybe. Star Trek, sorry. So it was a long search for this planet, but finally its existence could be ruled out. And this time it was Newton's equations that had to be replaced. Albert Einstein proposed his theory of general relativity in 1915. And this theory could explain the motion of Mercury, and it also made very many other predictions, like the existence of black holes, which have since been confirmed. According to general relativity, mass here does curve space-time in a similar way that a heavy weight curves a sheet of rubber if we place it on it. In particular, general relativity explains predicts the existence of gravitational waves. These waves expand and contract time and space itself. However, since gravity is much weaker than the other three forces of nature, this effect is very small. It needs very heavy objects like in-spiraling and coalescing black holes and neutron stars to produce gravitational waves that could be detected. 100 years after their original prediction, however, gravitational waves were discovered at this 4-kilometer long large laser interferometry gravitational wave observatory, LIGO. So far, I've told you about many cases in the past where the intricate interplay between theory predictions and experimental observations has led to the discovery of more particles and also more refined understanding via theory how these particles interact. However, there's still some unexplained discrepancies. For example, we can look at the neighboring galaxies in the sky and see how the stars rotate around the center of these galaxies. Here, if we look just at what speed those move for different distances to the center, we find this curve here. But according to general relativity and all the matter we see in this galaxy, the curve should be more like this one. One way to explain this discrepancy is again by postulating a new particle, some dark matter, which doesn't interact with light, so we haven't seen it yet. But we haven't seen this particle yet in any other experiment. Similarly, if we look at the expansion of our whole universe, we find that this one is actually accelerating. To explain this with general relativity, we need a new form of energy called dark energy, and we have no idea what that should be about. Finally, we also don't have a theory of quantum gravity yet, a theory that would combine the theory of general relativity with quantum mechanics. But several candidates for such a theory propose new particles too. In the coming decade, you'll see a vast increase in the availability of high-precision experimental data. In 2 years, the Large Hadron Collider will receive an update, and data taking there is scheduled to start in 2029. Moreover, the third generation of gravitational wave observatories is planned to be operational in the mid-30s. This includes both much larger ground-based observatories as well as space-based ones. To exploit the full discovery potential of these experiments, we need theory predictions of equally high precision to compare the theory to the experiment and discover new physics that way. A key ingredient for calculating those theory predictions in fundamental physics are Feynman integrals. This is both for gravitational waves and for the LHC. However, these integrals are also a key obstacle. You probably remember from gymnasium that an integral is defined as the area between the curve, the graph of a function, and the x-axis here. And maybe you also remember some impression that integrals are generally hard to do. The challenge in calculating the these Feynman integrals at high precision is twofold. First, completely new classes of mathematical functions occur in these integrals, which stem from integral geometries here that replace the x-axis in this integral. And second, even in the cases where the geometries are simple looking and the functions are well understood, our theoretical tools for doing these calculations are vastly inefficient. The aim of my Sapere Aude project is to overcome this challenge, to produce the required theory predictions, to compare them to experiments, and to discover new, future exciting physics along the way. Thank you.